Good morning, everyone. Myself, Devika, working as assistant professor in the Department of Electrical and Electronics Engineering at Sri Muthukumaran Institute of Technology. Today, we have discussed the subject on MR 3452 Control Systems Engineering for 2021 regulations. Today, we are going to learn the topic State Space Framework. So, state space representation. Defining the state variables in dynamic systems and formulating the state variable equations. The advantages of using the state space methodology and visualizing the state space model through block diagrams. And exploring system controllability and observability. Extracting the transfer function from state space equations. And it analyzing time response and the role of state transition matrix. Last one, understanding eigenvalues and their significance. Introduction. The state space framework captures system behavior through a set of interconnected first order differential equations involving internal variables called state variables. Alongside these, algebraic equations link the state variables to measurable output variables, providing a complete description of the system's dynamics. Understanding system state. So these are the input u1 of t, u2 of t, r of t. Output is y1 of t, y2 of t, yp of t. The system state is represented by a set of variables known as the set of state variables or collectively as the state vector. The total count of the state variables corresponds to the number of integrators present in the system, which defines the system model. So consider a system with multiple inputs or outputs that contains and integrators. General state representations. So the state representative we have two equations, state equation and output equations. So the state equation represents x dot of t is equal to, one-time differentiation of x is equal to a into x of t plus b u of t. The output equation y of t is equal to c into x of t plus du of t. So x is a state vector. We know that x dot is equal to d into x of t divided by t, derivative of the state vectors. Then u is the input vector and y is the output vector. So A is state matrix, system matrix, B is input matrix, C is output matrix, and D is feedback matrix. Then state space model to state transfer functions. The state space model, we know that x dot is equal to ax plus bu, y is equal to cx plus du. So by Laplace transform, s into x of s equal to a into x of s plus b into u of s. So we have to find x of s equal to, so s I minus a in the whole inverse b into u of s. Likewise, output equation y of s equal to c into x of s plus d into u of s. So we have to find y of s equal to the similar to the input equations. So then the transfer function is t of s equal to y of s divided by u of s. So equal to c into si minus a in the whole inverse b into b plus d. It's a transfer function of this state space. Then controllability. So a system is said to be controllable if it is possible to move the system from any initial state to any desired final state in a finite amount of time using a suitable control input. For a linear state space system, x dot is equal to ax plus b. So the system is controllable if the controllability matrix has full rank. So see, we have to find the controllability matrix Q C is equal to b a square b till a power n minus 1 into b. So the rank of matrix we have and then we have to find the rank of matrix. So n is the number of state variables when the system is completely controllable. Then observability. A system is said to be observable if the internal states of the system can be completely determined from its output measurements over a finite period of time. So for a linear state space system, x dot is equal to ax plus bu, y is equal to cx plus du. So system is observable if the observability matrix has full rank. So CA square till CA power n minus 1. So that we have to find the rank of matrix also is equal to n. So n is the number of state variables when the system is completely observable. Controllability observability theorem 1 and theorem 2. So theorem 1, x dot of t is equal to AC x of t plus b into u of t. So controllable canonical form to controllable. System in controllable canonical form is always controllable. Theorem 2 is the same. Observable canonical form is always controllable. So controllable canonical form that examines a specific state space model known as the controllable canonical form. This forms a crucial role when applying the pole placement technique in control system design, making it a fundamental concept to understand. Observable canonical form. It is a special state space representation of a system arranged so that the system is completely observable and the output directly reflects the internal states. Here, for an nth order transfer function, so the observable canonical form is state equation and output equations for this transfer functions. Then diagonal canonical form. In utilizing the diagonal canonical form significantly streamlines the process of deriving analytical solutions for system responses based on initial conditions. For the system x dot is equal to ax plus bu, after transformation it becomes state equation z dot is equal to az plus b. Then state transition matrix STM. It describes how the state of a system evolves with time from an initial condition. For the system x dot of t is equal to a into x of t. So the solution is x of t is equal to pi of t into x of 0. So pi of t here, pi of t is the state transition matrix. So definition, the STM is given by pi of t is equal to e power at. Then eigenvalues explained. For any square matrix of size, the eigenvalues are the special values of that satisfy Ax equal to lambda x. So characteristic equations to find eigenvalues and solve the identity matrix and determinant. Solving this equation gives n eigenvalues for real or complex. Then overview of state representation. So identify specific group of system variables to focus on, which are termed as state variables. For a system of order n, express the dynamics using n first order differential equation involving these state variables known as state equations. Then state space formulation for nth order linear differential equations. Let's examine on nth order differential system expressed as y plus a1y plus till an minus 1y plus an y is equal to u. The y represents the system output, u denotes as input signals, n is the order of the system, and n is the integrators. State space formulation for nth order linear differential systems. Okay, the final equation can be expressed as below. This is same as controllability and observability for example for your reference. This is another example for controllability and observability. So we have to find the state equations, I mean input equation and output equations also. Thank you.